So if you don't know what's happening in the terms of a sequence or a series, a good idea is just to start writing out the first few and see exactly what happens. And since it's the sine of n pi over 4 that we're trying to figure out here, since we might not be as familiar with that, let's just real quickly make a little table, a little list of the values of sine of n pi over 4 for some various values of n. And since our series starts with n equals 1, let's start ours with n equals 1. 5, 6. So now is when we ask ourselves, what is the sine of pi over 4, 1 pi over 4? Reach back to your unit circle trigonometry. Square root of 2 over 2. Great. So that term is positive then. How about n pi over 4 when n is equal to 2? So the sine of 2 pi over 4. That's up at the top of the unit circle. So that sine is equal to 1. Sine of 3 pi over 4, now that one's negative. The sine of 4 pi over 4, that's the sine of pi, 0. 5 pi over 4 is negative. 6 pi over 4 is negative. So something you notice right away is that this series is actually not an alternating series. Why not? Well, the 0 is a little bit of a tip-off. Yeah, I would say that the bigger red flag here is the presence of two positives, one right after the other, here, and then a couple of negatives, one right after the other over here. So in other words, the reason that you're having trouble getting this series to alternate is that it's in fact not an alternating series. In other words, the usual technique that we have to analyze alternating series, the alternating series test, is completely mute on this example. It's not going to tell us anything. It's not going to guarantee convergence. It's not going to guarantee divergence. It's not going to do anything for us. So since this is not an alternating series, when we use the sorting hat to try to figure out, what's going to happen with this one, then on the sorting hat, this is just going to fall right through the alternating series test. So when it asks the question, is it an alternating series, we say no. Which means we're going to have to analyze the series with a different tool. The alternating series test is not going to do it for us. So what can we do instead? How about a comparison? In fact, what simpler series would it be convenient to compare this series to? How does this series compare to 1 over n squared? 1 over n squared. So here's the idea. So where does that 1 come from, by the way? Why is 1 a good idea for a comparison? Say again?
Makes life easier.
Well, it makes life easier for sure. But how do we know that it's going to compare with our sort of complicated terms of our sequence? In particular, if we don't know exactly what sine of n pi over 4 is doing, because it's kind of sometimes positive, sometimes negative, sometimes 0, what can we say about the value of the sine of n pi over 4 for absolute sure? What's the largest value that the sine of n pi over 4 can have? 1. After all, the sine of any real angle can be no bigger than 1. So the sine of n pi over 4 is definitely less than or equal to 1. What's the least value that sine of n pi over 4 can have? Negative 1. Right? Because we saw the example where when n is equal to 6, we're at the bottom of the unit circle, and the sine of 6 pi over 4 is negative 1. But for certain, sine of n pi over 4 is never going to escape the range from negative 1 to 1. And since that's the case, when we divide every part of this inequality here by n squared, which is non-negative, in fact it's positive for n equals 1 to infinity, we find out that our sequence of terms that we're interested in is trapped in between the sequence of terms 1 over n squared and negative 1 over n squared. So this is a direct comparison. In other words, this isn't really a new topic in 10.4. It's only new because our series happens to have some negative terms in it this time. But with this comparison in hand, now what can we do? Now, the purpose of a comparison is to relate our complicated series to simpler series which we can tell whether they converge or not. So all we have to do here is introduce our sigma, introduce our summation sign on all three sides of this inequality. The sum, n running from 1 to infinity, of minus 1 over n squared. And then over on this side, the sum, n running from 1 to infinity, of positive 1 over n squared. And then in the middle, we're going to have the sum, n running from 1 to infinity, of sine of n pi over 4 over n squared, which is what we're really interested in. So what can you tell me about the series that are on the outsides of this inequality? What does the sum of 1 over n squared do? It converges because? Yes, the p-value here is 2. So it's a polynomial series, and its exponent is greater than 1. Therefore, it's a convergent series. How about the summation of negative 1 over n squared? Actually, summation of negative 1 over n squared does not alternate, because every one of its terms is negative. It's negative 1 plus negative 1/4 plus negative 1/9 plus negative 1/16, and so on. So actually, it's even simpler than an alternating series. One thing we could think to do is just to take this negative sign and put it out front. So I really have the opposite of the sum of 1 over n squared, n running from 1 to infinity. And what does the opposite of the sum do? Converge or diverge? This converges as well, because it's the same series that we had on the right-hand side. The only difference is that we're flipping the sign on every term. But it's still, its terms are approaching 0 at a polynomial speed with p equals 2. And p equals 2 being greater than 1, we get a convergent series on the left-hand side. So what that means is that the value of this infinite series on the right is finite. In fact, we don't need to know this, but its value is pi squared over 6. Whatever, the point is that it's a finite number. It's less than infinity. And likewise, the value of this series on the left will also be finite. It's actually the opposite of the value that we have on the right, minus pi squared over 6, which is, again, strictly greater than negative infinity, if you like. So because we have a convergent series on the left and a convergent series on the right, our series has a value that remains finite. And its terms happen to be going to 0, which we can verify. So with that, I think we can conclude that this series in the middle converges.